For 0.2, our two learning goals are, I understand and can use functions, inverse functions, and piecewise functions. And the second one, I can perform function transformations. We're going to start with just some definitions. The first one is a relation. It says any set of ordered pairs or a set of points on a graph. So an example of that, if you just take, like I'm just going to put 3 points up here. If I had like 2, 1, 3, 3, and 4, 1. This is an example of a relation, right? It's a set of ordered pairs. If you look in there, it could also just be points on a graph. Like if you think of a graph of a line, it has an infinite amount of points on it. And all those points would fall into this set, which we would call a relation. Function. A function is a special type of relation. Y is a function of x if for every x value there is only one y value. So what we mean by that is think of the x as the input. If I put 2 in, I get 1 back out, just one thing. If I put 3 in, I get 3 back out, just one thing. If I put 4 in, I get 1 back out. So this is an example of a function. Now if I were to add another point, let's say I added the point 2, 5. Now it would not be a function because when I put 2 in, I get 1 out, or I could get 5 out. I get 2 different things. So that kind of hopefully illustrates the difference between a function or not. It says you can use the vertical line test to test that. Think if I were to graph those 3 points. If I had the point 2, 1, 3, 3, and 4, 1. If we take a vertical line and run it across there, it should only touch each of those points once. There's once, 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 we're good. If I add that other point I had there, which was 2, 5, it'd be right there. Now as I run my line across, you see how it's going to touch twice. So you can use that vertical line test to see if something's a function. This is right here, f of x is function notation. So you can write it in the y equals form or the f of x equals form, but f of x and y are the same thing. Domain. Domain is a set of all the x values. So on this one I put down here, the domain would be 2, 3, and 4. The range is a set of all the y values of a function. So 1, 3, and 1. It would be the range. Let's look at these examples. We're just going to say, are these functions or not? There's a couple different ways you could look at it. One is you could think if they're graph. If I minus the x over, I get y equals negative x plus 1. If I graph that, it crosses at 1, and the slope's a negative 1, so I go down 1 over 1. Okay, so if I run a vertical line across that, that definitely passes the vertical line test. It only touches once as I go across there. Another way you could think of it is if I take a number and plug it in there. Let's say I plug a 2 in for x. I'd have 2 plus y equals 1. So I put 2 in for x. Well, how many y's do I get back out? Well, y has to equal negative 1, right? If I minus that 2 over. So when I plug 2 in for x, I only get negative 1 out for y. And it doesn't matter how many times I plug 2 in, I'll still get the exact same thing back out. So for every x, there's only going to be 1 y. So you can kind of think about the structure of the equation, and you're asking yourself, if I put an x in, how many y's do I get back out? This next one definitely is not a function. You can see it touches twice all the way across there. If you want to think about the structure of the equation, like when x is 0, if I put 0 in for x, you get 0 squared plus y squared equals 1. So y squared equals 1, I take the square root. When you do that, you have to put a plus or minus in front. So when x is 0, y equals plus or minus 1. Well, that's that point, 0, 1, and 0, negative 1. So for 1x, when x is 0, I can get 2 different y values back out, right? I get 1 and I get negative 1. Okay? So this would not be a function. 3, I don't know if you remember what this graph looks like. This is a parabola. It's shifted up 1 and it's opening down. That's what the graph looks like. If I do that vertical line test again, it does pass it. So this is a function. If you think about the equation, pick a number and plug it in there and think about what happens. Say I plug 2 in there. I'd get y equals negative 2 squared plus 1. That's negative 4 plus 1. I plugged 2 in. I only got 1 value back out. And it doesn't matter what you plug in for x, you always just get 1 thing back out. So it is a function. This one, x plus y squared equals 1. That one, let's plug a number. And if I put 0 in for x, I'd get y squared equals 1. take the square root, y equals plus or minus the square root of 1, which is 1. That means I got two answers back out. I put 0 in for x, and I got 1 back out. Put 0 in for x, and I got negative 1 back out. So it can't be a function. For 1x, there's 2 y's. By the way, that graph, when you square the y, is actually a sideways parabola. Doesn't want to draw that. So we're going to shift it left one, put a point right there if it will let me. And that parabola is just opening that way. Which once you have that graph, you can see it definitely does not pass the vertical line test. So you can think of the graph, you can think of the structure of the equation. If I put an x in, how many y's am I going to get back out? Here's some function notation. You guys have done this a lot before, right? If I want to find f of 10, that just means to take what f is and plug 10 in for x. I'd go 3 times 10 minus 1. So f of 10 is equal to what, 29? Okay, this next one's kind of funky, a little weird. You got x plus delta x. Delta x is just a variable, kind of like y or z. So what that means is I'm going to take x plus delta x, and I'm going to plug that into g for x right there. So let's plug that in there. I get x plus delta x squared. I could multiply that out, but it doesn't really simplify it at all, so I'm just going to leave it like that. There's my solution. So again, all you're doing is taking what's inside of the parentheses, and you're substituting it in for the x into the equation. Hey, 7 and 8 are what we call the composition of functions. So if you look at 7, what it wants me to do is I take g of, and I plug x into f first, and then whatever I get back out, I plug that into g. So if I plug in x into f, well, that's just, f of x is just 3x minus 1. Okay, and now I take what that is, this, and I plug it in for x up there in g, so that would equal 3x minus 1 squared. And that's my answer. Now, just to remind you of something, I'm going to multiply this part out. You don't have to in general unless it tells you to. If I do want to multiply it out, we go 3x minus 1 times 3x minus 1. I just have to distribute there. So this would be 9x squared minus 3x minus 3x plus 1. So if I simplify that a bit, I end up with 9x squared minus 6x plus 1. Okay, so that's one way to multiply that out. What I want to be careful of is don't just square the 3x and the 1. Like that is not, you're missing a middle term if you do that. The shortcut, if you want to use it, is you square the 3x, that's 9x squared. You square the 1, that's a positive 1. And then you times them together, minus 3x, and you times by 2. So that's a shortcut. This is called a squaring a binomial. It's got two terms. So you got to remember that middle term if you're going to use the shortcut. Or you can just multiply it out that way. You get the same answer. Okay, let's do number 8. Number 8 is also the composition of function. It's written just a little bit different way. That means, that open circle means f of g of x. The first one goes on the outside, the second one goes on the inside. So again, I take x and plug it into g. G of x is equal to x squared. So now I have f of, I'm plugging in what g of x is. Okay, now I come up to f of x, and I'm going to replace the x right there with x squared. So 3 times x squared minus 1. So 3x squared minus 1. Okay, so function notation, you need to know how to do that. You need to know how to do composition of functions. That's all really important stuff you need to review. This next part says find domain and range. I'm just going to focus on the domain on these three for now, and then when we get to the graphs, we'll come back and talk about the range a bit. When you talk about the domain of a function, you're asking yourself, what can x equal? Well, usually x can equal anything unless there's some kind of restriction. So there's two main restrictions we have to be careful with. One is a square root. If I have a square root, you cannot have a negative. So no negatives. Cannot have negatives inside of a square root. So that means it has to be 0 or bigger. So to find the domain, this is what we do. Well, x can normally be everything unless I get a negative. So I'm going to take x minus 1, and it has to be greater than or equal to 0. Well, if I solve that inequality, I have my answer. So I'm going to add the 1 over x is greater than or equal to 1. Right, think about that for a second. If I plug 1 in, 1 minus 1 is 0, square root of 0 is 0. If I plug 2 in, 2 minus 1 is 1, square root of 1 is 1. If I plug 3 in, 3 minus 1 is 2, square root of 2 is a decimal. But if I try plugging a number smaller than 1, like 0, I get 0 minus 1 is negative 1, square root of negative 1 is not a real number. So that's my domain right there. So if you have a square root, always take the inside, and it has to be greater than or equal to 0. By the way, if I use interval notation, I would say x can be 1 or bigger, so 1 to infinity is the way I'd write that same answer with interval notation. The second thing you have to be careful with is if you have a fraction or a rational. A rational means you have an x in the denominator. So if I have an x minus 2, now I have to worry about getting a 0 down there. Right? It can be a negative, that's fine. If I plug in negative, if I get 1 over negative 4, it's just a negative 1/4. But what can't happen is I can't get a 0 here. So if there is a rational, a fraction, I take the denominator and I say it cannot equal 0. I'm going to solve that. I'm going to add the 2 over. So x cannot equal a positive 2. X can be anything else. It doesn't matter. It can be negative. It can be positive. It can be 1. It can be 0. But I can't plug 2 in because when I plug 2 in, I get a 0 in the denominator. So the way I write that answer is I say x cannot equal 2. That's one way to write it. So that means it can be anything but 2. Or I can write it this way. It goes from negative infinity to 2 with a parenthesis because it cannot equal 2. I do a union, and then it goes 2 to infinity. This and this are the same thing. On 11, let's do domain and range because we have the graph. So if I do the domain, kind of think about tracing along the graph. Go from left to right. The graph goes until I get to 0, and it never gets to 0. There's a vertical asymptote along there. So we know that x cannot equal 0. Then it keeps going past 0, and it goes until I get to right there. There's another vertical asymptote, and that's at when x equals 2. And then it keeps going to the right. So basically the graph can be anything but, x can be anything but 0 and 2. With interval notation, you would say negative infinity to 0, union, 0 to infinity, or sorry, 0 to 2, union, and 2 to infinity. Hey, with the range is the y values. So if I have the graph with the y values, I'm just going from the bottom up. So if I start down here, the graph goes up, it's coming up both directions, which is fine. So it covers all the y values down here. As it gets closer to 0, you have an asymptote. It's like a horizontal asymptote, it does not cross it. So I'm going to write the range down here. I would say y now could be less than 0. I'm not going to put an equal sign because it never gets to 0. Or once you get between there, once you get past, I'm going to kind of think of this as vertical line. So think of a vertical line going up here. It can be anything until I get to 0. Then there's nothing until I get to when y is 1. So y could be greater than. Now ask yourself, does it actually hit 1? It looks like it does. So I'm going to say y can be greater than or equal to 1. Right? Then it just keeps going up from there. The way you'd write that with interval notation is you would say it goes from negative infinity to 0, parenthesis, because it never gets to 0. And then it starts again at 1 and goes to infinity, going that direction. So that's thinking of domain range. We'll come back and talk about the range of these two. We'll think more about the graphs when we do that, though. Okay, a one-to-one function. So we said for a function, for every x, there's only one y. But the y's can repeat themselves as long as when I plug in an x, I only get one. You can get the same y out every time. Well, a one-to-one function actually has to go both ways. So not only is there, for every x, there's only one y, but for every y, there's only one x. It has to go both directions. So for example, this is a function. If I plug 2 in, I only get 1 back out. If I plug 3 in, I only get 1 back out. If I plug 4 in, I only get 1 back out. This, however, is not a one-to-one function because now you're thinking backwards. If I plug 1 in, well, I could get a 4 or a 3 or a 2. So for that one y value, you have 3 different x values. So this is a function, but not a one-to-one function. Well, it turns out that one-to-one functions, it has to pass a vertical test to be a function, but it has to pass a horizontal test to be a one-to-one function. And we'll talk about that here in just a second. I'll show you some examples. An inverse function. When you find an inverse function, you take the x and the y and you switch them, and then you solve for the new y. The notation, if I want to say the inverse of f of x, I use that little minus. That's not an exponent, that's saying the inverse of f of x. You can actually also do this. You can say the inverse of y. Okay, so only one-to-one functions have inverse functions. And the reason why is because when I switch the x's and the y's, there has to be, for every y, there has to only be one x, so that when I switch it, that still holds true. So for an example of that, if AB is a point on f, that means that BA has to be a point on the inverse, right? The x and the y just have to be switched places. This next question then wants us to go back and look at those first 4 examples we did and decide if the function has an inverse function. So let's go back and look at those. Okay, so if you look at this first one, what you're really asking yourself is, we know number 1 is a function. The question is, does it pass the horizontal line test to make it a one-to-one function? And it does. If I run a horizontal line across, it only touches once. So number 1 is a one-to-one function. Number 2 was not a function to begin with, right? It doesn't pass the vertical line test. It actually doesn't pass the horizontal line test either. Number 3, if we think back to what the graph looked like, I erased it. Let me regraph that up here. It's a parabola, shifted up 1, opening down. Okay, that was a function, but if I do the horizontal line test, it touches twice. Okay, that means that it's not a one-to-one function. If I were to find the inverse and switch the x's and the y's, it ends up looking like this. Well, that's not a function, right? And the reason why is because it didn't pass the horizontal line test. So 3 is a function, but not a one-to-one function. Number 4 wasn't a function, right? We had this graph over here. It didn't even pass. It wasn't a function to begin with. Okay, let's swing back to there. Next thing is to show you how to find an inverse. Find the inverse of f of x equals 2x cubed minus 1. So here's your steps. Step number 1 is you replace the f of x with a y. So I'm going to write it as being y equals 2x cubed minus 1. Step number 2 is you switch the x and the y. So x equals 2y cubed minus 1. Notice how the 2 didn't move the minus 1 or the cube. It just switched the actual x and y. Step number 3 is to solve for y. So I need to get y by itself. So I'm going to add the 1 over. X plus 1 equals 2y cubed. Divide by 2. So y cubed equals x plus 1 over 2. Take the cube root of both sides to get rid of a cube. When you take the cube root of both sides, you do not need to worry about the plus or minus. It's only on square roots. So y is equal to cubed root of x plus 1 over 2. The last part is just notation. I don't want to say that this is the inverse of f of x. So the way I write that is I say the inverse with that little symbol, if that's the inverse symbol, of f of x equals cubed root of x plus 1 over 2. It's supposed to be an equal sign there. Okay, and I found my inverse. So again, steps: replace the f of x with y, switch the x and the y, solve for y, write it with the correct notation. Okay, so finding inverses. Piecewise functions. This is something you did in Math 2 and in Math 3. A piecewise function is that's defined differently on different pieces of its domain. So what I mean by that is, if x is less than 0, up here, right, we use y equals x. Right? So right here I have y equals x. That's when x is less than 0, right? X is 0 right there, and then to the left. If I'm between 0 and 1, so I'm between 0 and 1, I use this 2 minus x. Oops, let's do that different color actually. We'll make this look neat. So we're doing 2 minus x if it's between 0 and 1. So I come up here, between 0 and 1, I graph that equation right there, y equals 2 minus x. I want you to notice the first one, the one in red, had an equal sign. That's why there's a closed dot right there. This one did not have an equal sign, so I want you to notice the open dot here. And there's an open dot there, but here's what happens. The next one, when x is greater than 1, I graph x squared. So that's this part right here. It starts right here. So now that point's filled in. That's why that point was filled in, and it's going up that direction. So all you're doing is on certain parts of the domain or certain intervals of x, you're graphing different equations depending on the piecewise function. So let's actually practice graphing one. So this says graph this piecewise function, give its domain and range. So f of x equals the absolute value of x if x is less than 1. F of x equals x plus 2 if x is greater than or equal to 1. So one way to think about this is you can start by dividing the graph. When x is 1, there's like a wall there. To the left of that, when x is less than 1, I'm going to graph y equals the absolute value of x. When x is greater than 1, I'm going to graph y equals x plus 2. I don't know if you remember what the absolute value graph looks like, but you can plug in some numbers. If I plug in 1, I get 1. By the way, notice there's no equal sign. So when I do that, I'm going to put a point at 1, 1. If I plug in 0, I get 0. If I plug in -1, I get 1. If I plug in -2, I get 2. It's this V shape if you don't remember that. That's what the absolute value graph looks like. So there's my left side of the graph. On the right side, I got to graph y equals x plus 2. That's going to be a line. I'm going to start by just plugging in 1 again. That's where this graph starts. If I plug in 1, I get 3. So 1, 3. And that's a closed dot because this one has an equal sign. If I plug in 2, I get 4. If I plug in 3, I get 5. It's just a slope of 1. So that one's headed out that direction. Okay. The dashed line, that boundary, it's not part of the graph. You can leave it there. It's just to help us keep everything in its right location. So there's an example of graphing a piecewise function. Zeros. The zeros of a function are what do you plug in for x to make y equal 0. When we write zeros, we write them as just, x equals 2 or x equals 5. Now it turns out that those zeros also form the x-intercepts. When you write an x-intercept, you write it as a point, the point 2, 0, the point 5, 0. So just know these, right, we find these things the same way. Like that, if it has a 0 of x equals 2, it has an x-intercept of 2, 0. But the x-intercept is a point, if you want to write that down below. The x-intercept is a point, right? So if the 0 is 5, the x-intercept is 5, 0. Okay, 15 and 16, we found zeros using the calculator in the last section. We're going to find them without it now. So to find the 0, I want to find out what makes y or f of x equal to 0. So I'm going to plug 0 in for that left side. And then I'm just solving this equation. Hopefully you remember how to do this. If we want to solve a quadratic, the easiest way is by factoring it. X and x, I want the factors of -4, that have to be -3. So it'd be a -4 plus 1. Right? I times them, I get -4, I add them, I get -3. And now if that times that equals 0, all I do is set each of those factors equal to 0. Solve those two equations, and I got my answer. This one would be x equals 4. This would be x equals -1. Those are my two zeros. Now, if I asked you to find the x-intercepts, you would say 4, 0, and -1, 0. So x-intercepts you write as a point. Zeros you just write as being list them. Okay, this one's a little kind of tricky. X squared minus 4 over x squared plus 4. I want to find out when that equals 0. Think about a fraction. If I have a fraction and I want it to equal 0, it will only equal 0 if the top equals 0. So I don't have to worry about the whole thing. All I have to worry about is the x squared minus 4. So I want to find out when does x squared minus 4 equal 0. So let's solve that. You add the 4 over. X squared equals 4. You take the square root of both sides. So my two zeros would be a +2 and a -2. Like, try it really quick. If I plug 2 and I get 2 squared is 4, 4 minus 4 is 0, over 2 squared is 4, 4 plus 4 is 8. Hey, 0 over 8 is 0. So it works. When I plug 2 in, it makes it equal to 0. If I plug in a -2, the same thing happens. A -2 squared is 4, 4 minus 4 is 0. So finding zeros without a calculator, if it's a fraction, to set the top equal to 0. If you have a function like this, usually we're going to factor, okay, in order to find that. I think I'll say that the rest of it is looking at parent graphs and doing transformations. I'm going to save this for a separate video. So let's finish this one up, and then we'll come back on the next one and finish up that last little part, because it's kind of doing something a little bit different. We're shifting a different direction, and we'll do those transformations then.